All right, let's go over number 21 and 27 from the homework. In 2001, a national vital statistics report indicated that about 3% of all births produced twins. Is the rate of twin births the same among very young mothers? Data from a large city hospital found that only 7 sets of twins were born to 469 teenage girls. Test an appropriate hypothesis and state your conclusion. Be sure the appropriate assumptions and conditions are satisfied before you proceed. So our null hypothesis is that P equals what? 0.03. And our alternative hypothesis is that P, is it the same, so does not equal 0.03. Okay. So it just says, is the rate of twin births the same? And so the alternative is not giving us a direction, right? Greater than or less than, so we're going to do a not equal to. Our P hat is 7 over 469. 7 divided by 469. That's 0.0149. So our conditions. We can't really say that it's a random sample, but we could probably say it's representative. So the sample is representative. We don't have any reason to believe that the people that go to this hospital are different from people at other hospitals when it comes to having twins. 469 is less than 10% of all teenage births, unfortunately. And we need to check NP naught and NQ naught. So we need to check, not did we have 10 successes and failures, because we didn't, right? In our sample, we only had 7 successes, which would be twins born to teenagers. But we need to see if, given the 3%, did we meet that condition? So what's 3% of 469? It's 14.07. So 14.07 is greater than or equal to 10, and 469 times 0.97 is greater than or equal to 10. 454.93. So since our conditions are met, a normal model is appropriate. I will use a one prop Z test. Yes. I would put the decimals. Yeah. They want to know that you actually did the calculation. Okay, so yeah, put the decimals. Okay, and now our calculation. Perform the test. The z-score is your p hat minus your p naught over the standard deviation of p naught, q naught over n. So that's 0.0149 minus 0.03. I prefer to use the decimal, not the fraction. And 0.03 times 0.97 over 469. Notice I'm using my hypothesized proportion in my standard deviation calculation. So this top is negative 0.0151. And the bottom, 0.03 times 0.97 divided by 469 is 0.00788. And I get the z-score is negative 1.917. Remember that this is called what? The z-score is called the test statistic. Okay. It's called the test statistic. Okay. Now, how do I get the p-value from the test statistic? Yes, normal CDF. And it's negative 99, comma negative 1.917. Because it's a not equal to hypothesis, if my z-score is negative, I'm going to do negative 99, right? If the z-score is positive, I'll do positive, and then I'll times by 2. Okay, so it's normal CDF, negative 99, the answer, and this is 0.0276 times by 2 because it's a not equal, that's a two-tailed test, so 0.0552. So that's in that gray area for us between 0.05 and 0.1. And so this is a judgment call. You can decide to reject or fail to reject, and either result would be okay. Okay, we're going to talk about a significance level, an alpha level today, and we'll set that before we do the test, and that will determine whether we reject or fail to reject. We don't have to worry about a judgment call. We make a judgment in what we want to set that number to. So, my p-value. So we'll interpret our p-value. Okay, and yes, the book doesn't interpret the p-value every single time. And you don't have to interpret the p-value and write your conclusion on the AP exam. We're doing it in the homework so that if you're asked, I've seen AP questions that only ask you to interpret the p-value correctly. So we have to get really, really good at interpreting that p-value and understanding what it means, okay? So if the true proportion of teens giving birth to twins, that's our context, is 0.03, is our null hypothesis. There is a 0.0552 chance, that's our p-value, of obtaining a sample proportion as or more surprising, as or more extreme, however you want to phrase it, than 0.0149. This is the probability of getting our sample or more extreme if the null hypothesis is true. Okay. Your probability, if the null hypothesis is true, it's the probability of getting your sample. Okay. That's what p-value is. Then my conclusion. Most people, when they can choose, at this point, choose to fail to reject so they don't have to make an interval, right? But you could go either way. So which way would we like to go? Reject or fail to reject? Reject? Okay, so since my p-value of 0.0552 is so small, I reject the null hypothesis. It's kind of hard to say the 0.0052 isn't small, right? There is enough evidence to convince me the proportion of teenage twin births is not 0.03. When we make the interval, we can't use the standard deviation from our z-score calculation because that is using p-naught. we have to use our sample proportion. So our interval would be 0.0149 plus or minus. Now here's a great example when we create our interval of 95%. 1.96, 0.0149, 0.9851 over 469. That's what my calculation looks like. I'm still going to do it in the calculator. I go to A, 1 prop Z int. I put in 7 for X, 469 for N. And I calculate. Nope, it's not in my interval. So our interval does not contain our null hypothesis, which is good. If our p-value was closer to 0.1, then we're more likely to have our interval contain the null hypothesis. So sometimes we have to go to 90% confidence if we reject it instead. So you want to adjust that if you get the null hypothesis in your interval. I upon 0.00395 to 0.0259. So I am 95% confident the true proportion of teenage twin births is between 0.00395 and 0.0259. Okay, so number 27, some people are concerned that new, tougher standards and high-stakes tests adopted in many states have driven up the high school dropout rate. The National Center for Education Statistics reported that the high school dropout rate for the year 2004 was 10.3%. One school district whose dropout rate has always been very close to the national average reports that 210 of their 1,782 high school students dropped out last year. Is this evidence that their dropout rate might be increasing? So what does that tell us about? Tells about your alternative hypothesis, right? So my null hypothesis is that p equals 0.103. And my alternative is that p is greater than 0.103. They're worried about whether it has gone up, so they're testing a greater than hypothesis. The p hat is 210 over 1782. Which is 0.118. Check our conditions. The calculator can only do the calculations for you. Calculate the z-score and the p-value. You have to do the rest by hand. So the conditions, the sample is representative. We assume that the sample from that school year is representative of other school years at the school they're trying to get information about. 1782 is less than 10% of all students. High school students, to be exact. And then 1782 times 0.103 greater than or equal to 10. 1782 times 0.897 greater than or equal to 10. 103, I have 183.55. And 1598.45. So since conditions are met, a normal model is appropriate. I will use a one proportion z-test. So let's see how this works with the calculator command. All right, I suggest you get your calculators out. You're going to want to know how to do this. This is going to save you a little bit of time. On each problem, it'll add up. So we're going to go into our stat menu. Over to tests. Stat tests. That's where we're at. This is the list of all the tests that are available in the calculator. We are going to do a one prop z test. Makes sense, right? A one prop z test. It asks for P naught at the top. That is, what is your hypothesis? So what am I putting in for P naught for this problem? 0.103. What am I putting in for my x? How many successes were there? 210. This number must be a whole number. If it told you 11% dropout rate, and you had to multiply that by 1782, you'd get a decimal. You have to round that to a whole number for this to work. It'll tell you error if you don't put a whole number in for x. And 1782 is my n. Now down here, it's asking what is my alternative hypothesis that we're testing? Are we testing not equal to, less than, or greater than? Greater than. The number one problem I find with students using the calculator is they forget to change this to the hypothesis they're testing. So make sure it lines up to what you're testing, and then hit calculate. Okay, make sure you have what I have in here, and I didn't record. It's recording, but it's not record. I don't know what's going to happen there. Calculate. There we go. There's the information. I'm going to have to check this video to see if it shows up. So, what does this give us? Gives us my z-score. Gives us my p-value. Tells you what the p-hat was, 210 over 1782, and it tells you what your n was. So, this is how we show our work when we do the calculator. We write 1 prop z-test. We underline it, and then we write down the information. And that's enough to show your work. You are allowed to have your graphing calculator on the entire test, multiple choice, and free response. Okay. You are allowed to use the calculator commands to perform these tests. Okay. But you got to know what you're putting in. And remember that there'll be plenty of multiple choice questions that ask you, is this the right calculation for the test statistic for this problem? Right? And it has the numbers plugged in, and you have to select the one that has the numbers plugged in correctly. That's why we always do them by hand for a little bit before we go to using the calculator shortcuts. So interpret my p-value. You don't actually have to write interpret p-value, but I do it for your notes, so when you look back at it, you can see which one is which. So how do I say this? If the true proportion of high school dropouts is 0.103. There is a 0.0196 chance of obtaining a sample proportion as or more extreme than 0.1178. Since my p-value is so small, it's less than 0.05, it's less than 0.02, we're definitely rejecting. And I forgot an important piece in this. P-value of 0.0196. The AP exam specifically requires you to link your conclusion to the p-value number. So it requires you to have the p-value number in your sentence. So since my p-value of 0.0196 is so low, I reject, can't spell right now, the null hypothesis. Is there enough evidence? Am I saying there is enough evidence? Yes, there is enough evidence. To convince me the true dropout rate at this school, is not 0.103. It's not the same as the national value. And the point of the interval is to say, I don't think this is what it is, this is what I do think it is. And here's the even cooler thing about doing it in your calculator. When we do the hypothesis test in the calculator, if I go back in, I rejected, so I need to make an interval. When I go down to my 1 prop z interval, it already inputs the data for me. So as soon as I do a 1 prop z test, the calculator automatically puts that info into the 1 prop z interval for you, and it's true of every test and interval, so that all you have to do is hit calculate, or change your p-value or your confidence level and then calculate. So it's already there, and now creating that interval at the end isn't as much work, right? We're just popping it into the calculator and spitting out the new value. So now here's a problem. My hypothesized value is in my interval. Right? Doesn't my interval contain my hypothesis? Yeah. Right? 0.103 is in my interval. So this is where we need to go back and say, all right, well, I can't say I don't think it's 0.103 and then say I think it's between 0.102 and 132. Because that includes my hypothesis. I just contradicted myself. Okay, so I'm going to change my confidence level. I'm going to go back in, and I'm going to change it to 90% confident so that I don't look silly saying it's not, but then including it in my interval. Does that make sense? And we can just write 1 prop z int 0.0105 2.10 or no 130. And I can say I am 90% confident. The true proportion of high school dropouts is between 0.105 and 0.13.